Hello, everyone. Today, we'll be talking about Lecture 6 in the AAPS e-course on Good Oral Candidates 101. Now, this lecture today will focus on vehicle selection for safety studies. My name is Dennis Leung. I'm a principal scientist at Merck & Company, and I'm pleased to talk to you a little bit about some of the formulation work and strategies that we do to support these types of safety toxicology studies. So for today's lecture, here are the learning objectives. So first, we want to do a quick overview of oral absorption. So I know there have been several other lectures in this e-course that discuss a more in-depth role of the different factors involved in oral absorption of drug candidates. I do want to give you a quick overview of some of those factors because they do play an important role when considering these safety toxicology formulations. Now, considering those parameters, we'll move on to the second objective, which is understanding the challenges in developing a pharmaceutical toxicology formulation, and really what constitutes an appropriate toxicology formulation. I will end this lecture with 3 different case studies, basically 3 different formulation strategies for a safety toxicology study. So the first will be influencing dissolution rate with a formulation involving a crystalline nanosuspension. The second case study will involve increasing the solubility of your drug using an amorphous solid dispersion formulation. The third and last case study will focus on alternative routes of administration to enable increased exposure to a target organ. So we're going to be mostly focused on oral administration of these types of drug candidates, but in certain cases you may want to consider different routes of administration, and we'll see that in case study 3. And I'll end with acknowledgments for everyone who's helped contribute to the data and information in these slides. So as a quick overview of oral absorption of drugs, I've shown you this schematic here. So in the bottom of this cartoon is essentially a mechanical representation of the GI tract. So the white circle on the bottom left is your drug formulation, so in this case represented as a tablet or a capsule. So upon administration orally, you swallow your drug capsule, enters your GI tract, where the capsule or tablet begins to disintegrate, releasing the drug molecules, which start to dissolve based on the dissolution rate, to give you drug in solution. Now, this drug in solution then can permeate through your GI membrane, this mucosa permeability, and get absorbed to the other side, which gives you your total fraction absorbed. So as you can see in this diagram, all the purple boxes really contribute to your fraction of drug that gets absorbed when administered orally. Now, the red boxes in this schematic show you factors that may negatively influence your fraction absorbed. So, for example, if your drug is metabolized in the mucosa layer in the GI tract, that may degrade some of your drug and reduce your fraction absorbed. Efflux transporters also exist in the GI tract, and so these are transporters that hold onto your drug and then pump them back out into the across the membrane back into the GI tract for excretion. And so efflux is something you want to avoid because that can also negatively impact your fraction absorbed. Now, even then, once you get some amount of drug absorbed, that fraction then enters the portal vein, which goes into the liver, and you might exhibit liver metabolism, where the liver may break down your drug, which further reduces the amount of drug that finally enters systemic circulation. So it's really drug in systemic circulation that allows the blood flow to carry your drug molecule to its target organ or its target receptor. So in terms of the formulation or pre-formulation scientist, when we're trying to optimize a formulation to give you better oral absorption, those boxes in purple are really the ones that we want to focus on. So that's dissolution rate, solubility of your drug, and permeability of your drug. And by understanding those factors, you can then design a formulation to optimize that fraction absorbed.